Good afternoon. So again, I apologize about yesterday. I actually kept, I had a good signal until around 9 o'clock and then lost power again. But I didn't want to start up if it was just going to crash again, just so frustrating. So hopefully you had a productive evening and day, and I'm going to complete regression now, and then we'll get on to some probability, some basics. So let's see how much we can get done. So whatever we get done will be on the test this weekend. So the test will be, well, I guess tomorrow. We still have class tomorrow, that's right. So we'll talk about it tomorrow. We still have class tomorrow. All right. We have time. So this is where we left off. I was telling you about the expression for the line, and we have to remember to put a hat on the y because it's not a line, it's a prediction line. So it's an estimate of those observations. And we should only use the line within the range of the data, not outside of it, too far outside of it. We can be a little bit outside of it, but not too far outside of it. Otherwise, that's a bad extrapolation, resulting in erroneous interpretations. So for instance, I gave you the intercept, and I said, look, this says when x is 0, in other words, the leg bone, there is no leg bone, and then the humerus is a negative. Doesn't make any sense. That's just mathematically where it crosses the line. Okay? And so this is the slope. If we want to plot this, you could just use the line to find 2 points and then join them. You don't have to use 2 points within the range of data. You don't have to go to the intercept. So are there any questions about this? So we just use the results from the example that we work with. Now I'm going to use Excel, but with another exercise, a different exercise, not this one. So I talked about the slope and the intercept, and now let's apply the prediction line. Let's take the prediction line and answer this question. Use the prediction line to predict the humerus length y when x, the femur, is 60 millimeters. So you have to plug in 60 for the x in this on the line to find what y will be. So notice that when x is 60, if you go back to the original data, when x is 60, let me take the data with me. Oh, I don't want to put it here. So this is the data here. So is x ever 60? No, see, x isn't 60. This one was x. And this one is y. So x is never 60, you see? So we can use the line to predict what is it when it is 60. And we find out it would be 68.1685 millimeters. So we're making an actual prediction of something we don't have. What is the residual when x is 59? Aha, that's here. When x is 59, y is 70. So we got to make a note about that. X is 59, y is 70. So this is an observation. Okay. So to find the residual, it's two steps. First, you need the predicted value. You got to do this again. You need to use this to find the predicted value when x is 59. And you get that here. So it's going to be 66.9638. So that's going to be the predicted value. So then you take the observed value. This is what we saw on the data, 70. So this is the residual. So now I ask you, is this observation above or below the line? Right, it's above the line. Because we talked about that before. For here, we did a little a review talking about observed minus predicted. This will always be a positive above the line. Oh my goodness, I hit that button again. Stop. I need to read the instructions on this thing. I don't want the camera. All right. I'm just going to see the options here. I just want to turn that off. Oh, well. Okay, so we said observe will always be above the line when the residual is positive. So that's what we figured out. So this will have to be above the line. Then I asked the question, are there any observations that are influential? Okay, I fixed it. Are there any observations that are influential or outliers? So how would you figure that out? The way you sort that out is you identify in your plot if there are any observations that sit apart from the rest of the data. Then you take each of those observations and you check. You leave them out of your analysis and see how much they affect the correlation coefficient and the line. If they have a substantial effect on those estimates, then you should call it an influential point and investigate it. In this case, there are none. There were none. They were all very close together. I want to say something about what? So I was going to say something. These are not the notes that I used. Should have made a note because I thought of something to alert you about. This is what we discussed last class. Maybe it'll come to me. All right, so that's what you do. You check if any of the observations seriously influence the results. And here was our graph, and like nothing was sitting apart. They were all very close together on the line. Aha, this is what I wanted to tell you. I just realized. So, what is R? Is R... This is what I wanted to ask you. Is R a statistic or a parameter? Okay, Valeria says a statistic. And the rest of you? Well, it is a statistics because it's computed from a sample. Okay, if it's computed from a population, then it would be a parameter. So R is a new statistic. We haven't talked about that term for a while, but R, like the mean and the standard deviation of the sample, are statistics. And so R estimates a parameter. R estimates, does anybody know the symbol for the population? The population correlation? That's right, Nivette. This is the symbol for this is the sample correlation coefficient. You would divide by n. All right. So what's next? Okay, so there's R and there's R square. R square is common in regression. It's often in output, statistical output, they'll report the R square. So R square is what? R square is just R squared. Now, when you square it, it has a new name. It's known as the coefficient of determination, and it indicates the proportion or fraction of the variation in the response variable that is explained by the explanatory variable. So for the fossil data, if you squared 1, you'd still get 1 or 100%. So it means that 100% of the variation in the length of the humerus is explained by the femur. So what you have to do is, when you interpret the correlation, the coefficient of determination, or the R squared, you repeat this statement: 100% of the variation in in Y is explained by X. So you replace that with whatever Y was, and you replace this with whatever X is. Actually, I'll just circle this. Okay? So below are all the questions that you need to know how to answer. You need to know how to make a scatter plot of two quantitative variables and verify if the relationship is linear. You need to know how to identify if it's positive or negative in trend. You need to know how to identify if it's a weak or strong linear relationship. You should be able to find R and the least squares regression line. You should be able to interpret the slope and the y-intercept. You should be able to find the line, okay? And do that. You should also be able to use the line to predict y when x is a particular value, even a non-observed value. So you should be able to use the line for a prediction. You should be able to calculate a residual for any value of x that was observed. Any value or any point that was observed. And you should be able to determine whether a value is an influential observation. And the proportion of the variation in y that is explained by x using the R squared. You should be able to say so. And then I leave out from this class, but I do mention in the notes, a discussion on the coefficients validity and reliability and whether the prediction line would be valid and reliable. By validity and reliability, I don't think I included mine. So validity refers to it being unbiased. And this is usually described with like a bullseye and the values being, you know, near the bullseye. That would be unbiased. Bias would be if they were really off the mark or all off the mark. Reliable refers to the observations being in the same place. Like, okay, so I'm going to say this again, you know, or like close together. I think that's the best way to say, like small variation. They're very close together around the bullseye. This would be reliable too. I should get a better drawing. So this would be reliable too, but bias, right? And one more drawing. What I'm going to do is call this reliable and unbiased. This one is this one is unbiased and reliable, just like I did there. Or let's do this. What I'm going to make is I'm going to change it into unbiased but unreliable. And the way I'm going to do that is making them more scattered. So there's a lot of variation. So it's kind of like the center is here, but they're all over the place. So unbiased is good, but unreliable is bad. Reliable is good, but bias is bad. Those are both good. And what's the last one? Both unreliable. Okay, so then to be unreliable and biased, your estimates would be all scattered. Well, I shouldn't go off the target, should I? They're off the target and they're all spread around. Okay? So what you want is you want to be at the target and tightly spread around the target. So what is a good value of r squared? Remember we had the discussion over here about what's a good r. It applies to r squared as well. I mean, you just have to take the square root. Remember we talked about what is a good r. It depends on the sample size. So if you want to know what's good r squared, take the square root and use the same rule here. All right. So I mentioned now we have all these parameters that we're estimating when we do regression: mean, standard deviation, the correlation coefficient of the population, alpha and beta, which are actually the population estimates of the population parameters that are estimated by A and B. And the idea is that there are a number of assumptions when we do this, and a major one is that that the expected value, the conditional probability, or the conditional mean, condition on each value of x has an expected value that falls on the line. So it's like saying that on average we hit the line. Okay, and there's another, like, that is tied together with the assumption that there is randomness in the error, or the residuals that estimate the error. So I'm not going to get into this, but this is basically the classical linear model and the assumptions of the simple linear regression model. I'm not going to get into that. I'm going to just leave it here for completeness, but we're not going to get into that. And then I start talking about the assumptions of the classical linear model that you need to have to ensure that you have validity and reliability of your estimates. And then I talk about adding another variable inside. So what you have is, this is the general model where you could add other variables as explanatory variables, and then there's assumptions about those that we have to consider, in particular that they're not correlated with each other. And then we add this E in, because you see, if I get rid of the hat, I have to add the error term in to make sure that I have these all lie on the line, they fall on the line. And this is the population model that we're trying to estimate. And as I say, we're not going to get into that very much, but I have some discussion here that might interest you. And I also talk about transformations. These are common in economics when you don't have, when your relationship is not a line but looks like something recognizable. So let's say you have a curve like this instead of a line. If you take the logarithm of y, you can actually convert it into a line. But again, I'm not going to get into any of that. So these are the common transformations . So you could log the variable, you could take the square root of a variable, and you could invert the variable that you want to transform. And you would do this when you don't have, when you don't see a linear relationship, and you want to depict one. So we're not going to get into that. I just put all that in for completeness. You can read through it. Maybe you've seen stuff like this before. See, these are some of the results of economics that are common. So essentially, I want you to skip pages 10 to 18. So we'll omit pages. I mean, you don't have to omit them. That's a strong word, but just say pages 10 to 18 will not be examined or tested. You'll not be responsible for those. All right, so then we have some review exercises, because essentially I'm done with the notes. Okay, so this is just a review of what we discussed. So in each case, for this exercise, explain what's wrong with the statement. There is an R equals 0.6 between gender of student and their scores on a statistics exam. What's wrong with that statement? Right, so gender is not quantitative data, right? So I gave that one away to you already. I explained that before. What about the next one? 1.09 between student scores on a math exam and a statistics exam. What's wrong with that statement? No idea. The fact is that R is between a -1 and a +1. So it can't be more than 1. That's not even possible. Okay, that's the mistake, or that's something to be looked into. R of 0.23 bushels was the correlation between the amount of fertilizer and yield of corn. What's wrong with that statement? No idea. The problem is the word bushel. There are no units. There are no units of R. It's just R. Since R equals 0.89 between cups of milk consumed per week and height, we know drinking milk makes you grow. What's wrong with that? That's right, Alexandra. I think the connection broke or something. Did you not hear me? The last one? There are no units for R. Okay, so for this one, cups of milk, the problem is, this might be high and everything, but that's just correlation. That doesn't mean one causes the other. I see your answers, they just come up late for me because there's a delay. Valeria, what rule are you talking about for the last one? I mentioned all of them. No comments? Okay. let's look at this exercise here. So aerobic fitness can be evaluated Sorry, I'm reading Validity's comments. I'm not sure what you're asking. Do you have a question? Okay. So aerobic fitness can be evaluated using a special test that measures the oxygen uptake of a person running on a treadmill for a prescribed distance. However, it would be more economical to evaluate fitness with pulse rate. Whether the running pulse is a better predictor than the resting pulse needs to be evaluated, however. Below you have data on oxygen uptake of 31 individuals before and after a 1.5 kilometer run. The individuals ran 3 times. You are given the average length of time for the run in minutes, the average amount of oxygen uptake, the average resting pulse, the average running pulse, maximum pulse, and descriptive statistics such as sex, age, and weight. We want to investigate whether the average resting pulse or the average running pulse rate is better at predicting oxygen uptake. So here are the graphs. And what do you say? How do you comment? Is running pulse a better predictor than resting pulse of oxygen uptake? So there's a negative relationship. And is it weak or strong? So as running pulse increases, so the person runs, and as their running pulse increases, the average person's running pulse is increased, there's less oxygen uptake, right? It's harder for their lungs to get oxygen. Now this scale is higher than this one because here they're resting. So this is their pulse when they're resting, and even there when they're not even running, we haven't even had them run, we just measured them 3 times while they were sitting. And there as well, the higher their resting pulse, the lower their oxygen uptake. Right, so they're both linear relationships, but they're both weak. And the way we see that is look at the R square. The R squares are about the same. So this means 15% of the variation in oxygen uptake is explained by running pulse. And the same thing here with the resting pulse. 15%, that's quite low. We have 31 observations. I think, remember when we did it in class, for 100 observations, you needed at least 0.2. So this is a very weak relationship. You could also calculate the R square, which I want to explain to you. Not the R square, the R. If you want to get the R from the R square, you have to take the square root of this number. So let's do that. So we had to get 20.2, sorry, 0.2 for R if there were 100 observations. This is only 30. So let's just get the R here. Don't forget though, the R would be a negative. When you have to get the R from the R square, you have to be careful about the sign because this goes down. So if we took the square root, one, 5, 8, 3, 8, 3, you get like 0.4. So R is 0.4. So we'll need to check. Let's check our rule about R has to be greater than, what was it, 2 over square root of n. That was the rule, right? So it would be 2 divided by square root of 31. So this ends up being 0.36. So it actually does exceed 0.36, but it's close to it. So this is a weak relationship. And so both of them, there's no difference between them. If there's no difference between them, we should probably go for the cheaper one. But we're comparing this to what are we comparing this to? Below you're given So what we're trying to say is we have a special test to measure the oxygen uptake, and we're going to substitute either of these for that more expensive test, and no one is better than the other. So if it's economical, it doesn't really matter which one is that you use. They're both about the same. Any questions? All right, so I did A and B. What about C? Oh, the questions are here. So C, the least squares regression line was fit to the data. Find the equation for this line in your output. So the equation in the output, I could highlight it here and here. And what you see is that the y-intercepts are different because this is for running pulse, and I guess they need more oxygen, right, when they're running. So this is going to end up being a higher intercept than this one, but the slope is about the same. The slope is about the same. What about D? What is the y-intercept? So then you read the y-intercept and interpret it, and then the slope. So if you interpret the y-intercept, here it's 82, and it means when the when x is 0, y is equal to 82. When will the running pulse be 0? The running pulse will be 0 when a person is dead, so this is not realistic at all. The person won't be breathing, but mathematically that's what you would get. So you'll notice here that the scale of these graphs is not even near 0, right? The software plots it only around the range of data. These are not at the origin. Same thing over here. This doesn't make sense, but it is mathematically the intercept. Sorry. Again, same thing. If x equals 0, that's your pulse, then you're dead. So this doesn't make sense that your running pulse would be, that your oxygen uptake would be 62. You wouldn't be breathing. Questions about that? All right, so part E, the slope. Let's try the slope. So for each, to interpret the slope, we say for each additional unit of the running pulse, oxygen uptake decreases by 0.2. That's the interpretation. And here, for each unit of increase of the resting pulse, oxygen uptake decreases by 0.28 units, whatever the units are. So you can learn that expression. For each unit of increase in the average pulse rate following a run, the average oxygen intake level is reduced by 0.21. So in general, you would fill in X, and then here you would fill in Y, and then here you put the slope. It's always like that. So same here, for each unit of increase in the average resting pulse rate, the average oxygen intake level is reduced by a unit of 0.28. Reduced is the negative. Anything else? What about F? Okay, what's the correlation coefficient? We calculated it, right? We took the square root and attached the sign. So neither is as good as the other. Question G, what would be the effect of using the recorded measures of the actual resting pulse and actual running pulse and the actual oxygen uptake? Oh, okay, so this is asking not the averages, the actual recorded measures. What would be the effect? So we average for every individual, the measures were averaged and then plotted or recorded and plotted. What if we use the actual original data? How would that look different? And how would it affect? How would it affect our analysis? Why is it easier, Nivette? Or are you asking me? You're asking me if it's easier? The reason we use averages is because averages will stabilize our data. Using the original data will make the data more scattered and the correlation less like weaker, even weaker. All right, so you actually have 100 observations if you use almost 100 observations if you use all the data. But the truth is the correlation based on the individual data would likely be lower. The scatter plots would have data that are more spread out, okay, more wild. So that you wouldn't want to do that. Here I've shown you, I show the origin of the data, and even in the statistical software, they do not extend the line, but you could to see that intercept, but there's no need because we're never going to make estimations over here. That's what I have in this yellow box. It's very hard to read, hey? I should fix that. Anyway, maybe you have a good version of my notes. The PDF distorted some of the notes here. Okay. So that's that. Any questions about that? Now this third exercise. To combat automobile pollution, a study was done to determine the chemical composition of gasoline additive that will improve emission quality. The study examined the relationship between the amount of a particular additive and the reduction in the emission of nitrogen oxides. The amount of nitrogen oxides in the exhaust of each car was measured first without the additive and then with a specified amount of the additive. The reduction in nitrogen oxide in the exhaust was the response variable. So, this is the amount of additive. This is the reduction in nitrogen oxide. So you're more successful at reducing nitrogen oxide the more the additive. So this is a positive relationship. This is the scatter plot here. And you see the regression here, the R square here, indicating 89% of the variation in the reduction in nitrogen oxide is explained by the amount of additive. So that's really good. So it means that there's not, that additive is doing a great job of explaining. There's not a lot of explanation by unknown or unspecified variables. So what's next? Oh, and let's look here. It's a very tight positive relationship. So it's a strong, linear, positive relationship. And we have the regression line. Let's see what the questions ask. So make a scatter plot, fit the least squares line, highlight the equation. What is the predicted reduction of nitrogen oxide in the exhaust when the amount of additive is 3? So the observed value is here. So when you have 3 units of the additive, you have 3 units of reduction in nitrogen oxide. But what about the prediction? How is the prediction? So let's see if we can make a prediction using the line. So here's the line, and now I'm going to predict using the line, substituting 3 for x, and I get 3.163. It's pretty close, pretty good prediction. So what's the residual for that observed value? So I have to take observed minus predicted, right? Y observed. So one way to remember, I had to do this when I was a student, not to mix it up. To remember observed minus predicted and not the other way around is just remember the alphabet. L, M, N, O, P, right? Statistics, we like to do things in alphabetical order. That helps a lot when you realize that pattern. So observed before predicted because it starts with an O and that one with a P. So observed is the 3, and the predicted is 3.163, so this is the residual. So that means, what does it mean? It means that the observed value is under the line, right? Because it's a negative residual. So what's the next question? Okay, make an estimate. It says, what about if, what is the predicted reduction when the amount of additive is 15? So 15 is not on our list. It's actually double the highest amount of additive. But if we put it in and we assume that the line explains the relationship even in for values double the range that we have, we would get that it's reduced by 7.807. But you have to be careful. This is a case of extrapolation since the value of 15 is far outside the range of values. I repeated myself. 15 is far outside the range of values for the amount of additive that were used to obtain the line. The prediction is not likely to be accurate. So what happens is then I introduce the concept that, well, these scientists had funding to actually to make another estimate, or another measure. They use an additive of 16 units. So that's outside the range, like the 15 that we imagine. So let's use 16 and see what happens. It turns out that the reduction in nitrogen oxide was 5. So if you use 16, you get 5. So that doesn't look like a linear relationship, right? This is double, and that's just about the same. So what happens now we have an observation that is over here, away from the rest of the data, when the data would have predicted it would be up here. If I was to take this with me, that's not what I wanted to do. So if the line applied outside the range, we would expect that the line would continue to explain the data out there. That's not what I wanted to do. I need the other graph. I took the wrong graph. Let me do that again. I want to get this one. All right, so this is the original graph, and so if we believe that this relationship continued outside the range of data, then we believe the line would just continue outside the range of data. And then for 16, let's take the ruler back. And for 16, which would be like here, we should get an observation. We expect our prediction line would be up here. Our prediction would be up here. But that doesn't happen. It ends up down here, and then if you compare the original line with the new line, it slants the line, it changed the intercept, it changed the slope, and the correlation goes down. Well, the R square goes down from 89, and now it is 67. So it really affected things. This would be an influential point. This is an example of an influential point. And you wouldn't want to use the line for data outside of, far outside of the original prediction. But how do we ratify, how do we rationalize, not rationalize, but how do we deal with the situation? Well, we could get more data. If we got more data, maybe what's happening is that there's a plateau. The more and more of the effluent that you add, it plateaus and doesn't have an effect. And you even want to check beyond that, because maybe it has even worse effect. Maybe it starts to even go down. Okay, so it just looks, as far as we're concerned, it just looks like it plateaued out. So depends on what you want to do. If you have the funds to get more data, to make a different estimate, and then use this curve to make predictions, or just advise not to use this estimate, the estimated line, outside the range of data to avoid making false claims about reductions by adding this amount in. So those are my suggestions there. Questions? Having some buffering going on. There's some sort of buffering. All right, any questions? Okay, that brings us to finance data. If you don't have any questions, I want to talk about this now. And then there's just a practice assignment. So let's just talk about this and then we'll do the practice assignment. All right, so here's some financial data. I refer to this as historical data, and I'm going to differentiate it from the ex-ante data that's below. And I did present data like this in GDS Unit 2 as well. So here we have returns to this market index. It tracks 500, the top capitalized, the most valuable companies that are public companies. In other words, you can purchase, not private companies. The public can purchase shares in the company, or even if they issue debt, that you can individual investors or corporate investors can purchase bonds issued by the company. So anyway, this is an index representing the stock valuation of the companies, and it shows the returns to this index. So it's a measure of market performance. So the market's doing well, second period it drops, it's doing all right, it drops again, and it's kind of volatile. So these are just periods. I'm not mentioning if it's a year or week or whatever it is. These are just a period of time that, because it's historical data, and it's already transpired, and I consider each of these equally significant or important in terms of information value. Then I have this returns here for this company. These are the stock returns of this company, BCE. Now you don't need to know the finance piece of this, but what we do is we make the market index the X, and we make the company or firm, any firm's stock returns the Y, okay, in finance. So I tell you this one's X and this one's Y, and then from there we can calculate the mean, standard deviation, and look at if there's a linear relationship between these two. So looking at this data, what is the relationship between these sets of data? Just looking at it, what do you think? Aha, Yvette sees it's double. So what does that mean? What does the double mean? So I'm going to ask you, what is R, without making calculation, what is R and what is B? What is A? What is Y equals A plus BX? So it looks perfectly positively linear, and Alexandra says that R is 1. Is that what you're saying? Yes. Very good. R is 1. What about B? What about A? So R is perfectly positively 1 because the relationship is exactly double. So it's perfect. You can predict one from the other. So you guys don't know anything else? That's it? Just R? Aha, so B is 2. So the 2 goes into the B. The B is the slope. So for each unit of X, this is what it means. So for each additional unit of X, Y changes by 2 units. That's what you're seeing. So that explains the relationship between X and Y. And A will be 0. Okay, very good. So there's no intercept when X is 0, Y is 0. So let's see. So I guess so then we know Y is equal to 2X is the relationship, and it's actually going to be perfect within the range, right? Now, all of these formula you should know. You should be comfortable with the covariance, the correlation as a standardized covariance, and then these other forms of it. And then this is the slope, RSY over SX. I could also write B as covariance XY divided by SX squared, or variance of X. So it's like the B for every unit of variance, it tells you how the variables, how they covary for every unit of the variance. So B is a measure of sensitivity of Y to X, how it responds to X. So we use a correlation type relationship because there's a theory based in doing it this way. And that theory has been established and reestablished that there's a relationship between market returns and influencing stock returns. And because of that, I get to rely on that theory and draw things this way and draw conclusions. So that's how it works for this finance data. So what I want to do is put this in our well, you could put this in your calculator and get those results. I want to go to the next set of data, and this is the ex-ante data. If you remember, we did do that back in GDS, or I left that with you for GDS review of the notes. And I want to calculate that in Excel. But if you guys want to check right now, put these values into your calculator and verify what I've said here. So I'll give you a few minutes to do that. First I have to get this off begin mode. And then go to my data and clear it, the second clear work, and start over. So I can put this information in as pairs of data, as percentage, or as decimals. Then I get my results. The mean is 5 for X, 9.9 is the mean, sorry, and the N is 5, 9.9 is the mean for X, standard deviation of 3, and that's the population one. I won't look at that. And then the mean for Y is 19.8, the standard deviation is 6, and I don't look at that. So then here's the A, 0, B is 2, R is 1, as I promised, just looking at the data. And like most of the time, you know, it's not easy to summarize, but it was in that case to see the results. Now, what about the second data set? So this is going to be for ex-ante data. In this case, what I have is a different representation of the data. I have a distribution that explains the data. So looking at maybe historical data and some models of the economy, this distribution is derived. And it says it's a discrete distribution. Not a continuous one. It's a discrete distribution because I only have 3 states of the world. So either the economy goes through a boom or expansionary phase, the economy is going to be normal state, or it's going to go through a recession. In the boom state, S&P will be 14% and BCE will be 30%. So they're both high in the boom state, and BCE is higher. In the normal state, with a 50% chance, so this is the most likely state, it'll be 8% and 18, so they're both down a bit. And then for recessionary state, the least likely, it's going to be 4% returns for the market and 10% for BCE. So how in the world do we analyze this? I want to find the correlation between these two variables. And then the regression line. So these are the formulas we discussed back then. This is the expected mean. This is the expected mean as a weighted mean. This is the standard deviation as a weighted standard deviation. And this would be, I'm introducing now the weighted correlation. Oh, sorry, the weighted covariance. Then this would be the weighted correlation, and this would be the beta. I guess it would be a weighted beta. So I use Greek letters all throughout here because I'm treating this as the distribution. It's not just some random data I collected. This represents, after, like I said, intensive study and modeling, I come up with this distribution of 3 states of the world. I believe it perfectly describes what's coming. So these are now what I believe will be the state of the world, and strong assumptions. But anyway, so I get to use my Greek letters because I believe these are parameters. So to practice this, before I go to practice this, I want to make a point about me calling B sensitivity. It's because even though these are all positive values, what if, using the line, what if the S&P was negative 10%? What would happen to BCE? Well, the relationship is double, so it would be negative 20%. If this line, I guess it's outside the range, but if we believe the line is consistent, let's not go, oh no, I'm going outside the range. But if we believe that that's the case and the line is consistent beyond the range of data, it would be, this would be the case. It would be double. So this is, B, the slope being recording the sensitivity also records the riskiness. So it's risky because on the upside things look great, but on the downside it's pretty bleak. Okay, so B is a measure of risk and that's why I adopt the mnemonic device risk. So you remember the formula RSY over SX. Okay. So if you translate, you go through the translation of all these variables to Greek letters, this is what you get here. Now to calculate this, you can't do this on your TI BA2 Plus. An HP calculator can do this, the HP 10B2. But what I really want you to do is use Excel for this. So I did give you some Excel worksheets in Moodle that you can practice making these calculations. Here is the sheet that I gave you for ex ante data, or ex post data, sorry, the historical data. And like I say, you can download the sheets and use them to practice making the calculations. And then there's also this one that I made for the ex-ante data, and you can download those. So those are in Moodle, and you should be able to practice to reproduce the values that I get for this exercise. It's a lot of steps, but you can do it. So, no, I don't want to leave, sorry. The answer here, it turns out, even though you can't really visualize this so well, it turns out that R here is also 1 and B here is also 2. So you can practice verifying that with the formulas using the Excel spreadsheet in Moodle or making your own. Any questions? So it does look intimidating until you do it. This is just the mean, right? This should just be mu here, mu. That's just mu of x. And this is mu of x, this is mu of y. So you're going to see this again when we get to the probability section. I'm going to reintroduce this towards the end of a probability unit. So learn it now. Save yourself the trouble. So for tomorrow, attempt to do this, calculating R of 1 and B of 2 for this data. Okay? And again, you don't have to do this by hand at any time. You know, for the test, you can use Excel. So practice using Excel. All right, that brings us to this exercise. So I'm going to ask you, if you haven't done it, work on this exercise. I'm going to give you 5 minutes to set it up. Okay, what did you get? Did you do that? What did you get? Or do you need me to do it? R equals 0.54. Nope. That's not it. Alexandra. Did you follow the instructions? Right, Valeria. Maybe Alexandra, you didn't follow the directions for the second part. Oh no, you did the first part. Okay, something went wrong there. So what you first have to do is compute the missing value. And you're given the information. So here you get 2 minus 4 divided by 2, and you put it in there. So that's negative 1. And then for this one, you use 17 minus 7 divided by 5, which is 2. And then you notice that all of these are 0 except a few of them. So when you multiply these together, you just get a bunch of zeros. Right, Valeria. And then, so these are all 0, 0, 0, 0, negative 2, negative 2, 0, 0. So you just get negative 4 as the total. And then you have to divide by n minus 1. So R is equal to the total divided by n minus 1. The total is minus 4, and n is 6. So 4 divided by 6. And we'll just round. It's 0.67 negative. All right? Yeah. So for the test situation, remember, keep your notes, and if there's a dispute, you can you'll send them to me, and I'll be able to see your error. If you convince me, I can consider giving you part marks. Okay, so we got this R of negative 0.67, but when I asked you to avoid carry through errors, I just said ignore what you did in part A and just assume R is 0.3 and now find the equation. Can you guys do that, or did you do it? What's your equation? What's your B and your A? Now, in a test situation, you can just, use your calculator. But if I want you to show you your work, this is just to show your work. But since we're at distance, I'm not going to be grading that. So we begin with the first point is that X bar, Y bar is on the line. So this is a point on the line. So X bar, Y bar is 4 and 7. They are 4 and 7. 4 and 7. The second fact is that the slope will be RSY over SX. So I'm going to use the value they gave me, 0.3. And since I changed the R, you can't use your calculator because there's no way of getting 0.3 with that data. So, you can't use the points above to get the right answer with an R of 0.3. So SY from there is 5 and SX is 2. So this is going to be 5 divided by 2. So your answer for B is 0.75. Or you could write 3/4 if you want. Right. Good idea. And the third thing to do is to find the intercept. And the intercept is found by taking the expression and plugging in what you have. We're going to use 7. We are going, because the line should be satisfied for all the points on the line, then this point must satisfy the line. It must fit on the line. So to find A, we plug in the point and the slope that we have to find A. So A is equal to, I can put 3/4 and 4, and you see that simplifies things so nice that I can cancel my 4s, and then I see clearly that A is 7 minus 3 or 4. So my final answer is Y hat equals 4 plus 3/4 X. Or you could write Y hat equals 4 plus 0.75 X. And don't forget the hat and circle your final answer. Any questions? So what follows is a practice assignment with solutions. I was going to let's look at the homework. Did you start the homework or try the homework? I'm going to look at a few homework exercises that students often ask me about. No questions? So this is the homework set of questions. And without looking, how many of you have tried the homework already? Okay, let's try number 4. I'm also going to try 16 on 15 and 16. And if you have any others that you want to ask me about, you can ask me. So let's look at 4. Okay, Leanne, Jesse, let me know which ones you have problems with. So a study was conducted to examine the quality of fish after 7 days in ice storage. For this study, Y is the measurement of fish quality on a scale from 0 to 10, where 10 is the best and 0 is the worst. X is the number of hours after being caught that the fish were packed in ice. So presumably the higher, the more hours, the worse the fish, right? So that's a negative relationship because more of X than less of Y. So it's estimated that the linear regression equation is this. You see? It's negative. The slope will be negative. So let me say something about this. The slope is equal to r sy over sx. So isn't it true then that r and b will have the same sign? You need it bigger? Are you watching on your phone? So B and R have the same sign because SY and SX are both positives. They have to be because they are the square root of the variance, so they're both going to be positive. So that means if R is negative, B will be negative, okay? So this is showing a negative relationship, negative correlation, and the trend is a negative trend. So how do we interpret this? Which one of these is the way we interpret this? Oh, Valeria, maybe you can open two windows, one, like two browsers or two windows, and one with the chat and one with the video big. I don't know. I should keep that in mind to keep it big. Okay, anyway. What do other people think? Alexandra says A. What do you think? Okay, you all pick A? Or no, two of you picked A. That's right. Okay, so as X increases, Y decreases. That's what we see. So 1 hour delay in packing. So what you can do in the question is underline or circle the definitions, but here are the definitions right here. So X is the number of hours. So after being caught. So they summarize the word in the question as delay. Okay? And here is the quality. So Y is like in one word quality and X is delay. So 1 more hour of delay decreases the quality. That's perfect. A is the answer. All right, let's look at the next one. How about 5? No comments? All right, see your answers. Oh, look at the options. Okay, so here you have a correlation between the sex of a worker and her income. Problem with calculating R is that it's not the right statistic to make a relationship between gender and income, okay? That's not the right statistic. So D is the answer. This is nonsense because R makes no sense here. Now some of you picked E. What does E say? The correlation of negative 0.61 is not meaningful here because the relationship between sex and income is likely nonlinear. No, that's not the point. You just shouldn't calculate it, is the point. But you guys are close to knowing that it's nonsensical. It's not that it's not linear, it's that you're using that they're not quantitative. You want to look at 6 now? Let's look at 6. If the correlation between body weight and annual income were high and positive, what can we conclude? Body weight and income. Okay, all of the statements with cause should be eliminated because you can't say one causes the other, right? Unless you have an experiment or a quasi-experiment, some sort of adjustment to make it an experiment. But this is just a study that shows these two are correlated. So we're down to C and D. So process of elimination, it can't be any of those. So between those two, which one is it? So, you see a relationship and you do want to make some bold statements, but you're limited without a experiment. So we're going to say tend to. High-income people tend to spend a greater proportion of their income on food than low-income people. See, now there is no information here that their income was spent on food, was there? This is reading between the lines error, fallacy, I don't know what to call it. But it's actually D is the best answer. High-income people tend to be heavier than low-income people on average. Now you could speculate that it might be because, but you don't have any proof of that. All you have is that they're both high. All right, so the answer is D. You are just speculating that this might be the reason, but you don't have much. If you had to pick between C and D, your best answer is D. Okay? Now, this is common for people, you know, creative people will come up with answers, but we're not at that stage yet. You know, first we have to say this is what we see, and this is what we can speculate. How about the next one? If there's any that you want me to look at, let me know. Yes, Alexandra, it could be due to type of job instead of spending habits in the last one. Right. More sedentary jobs, less active, or more hours and after hours and less time to exercise could be responsible. Would you like me to review this one together? I mean, you want me to start? Okay. So a study examined the relationship between the sepal length and width, just call it length and width, for two variables of an exotic tropical plant. Variety A and B are represented by X's and O's. So this is A and this is B. Which of the following statements is false? Consider variety A alone. There is a negative correlation between length and width. Yes, that's true. So I'm going to put a T beside it. Considering B alone, the least squares regression line for predicting sepal length from sepal width has a negative slope. That's true. Considering both varieties together, there is a positive correlation between sepal length and sepal width. Well, if I was to try and put a line, it would go like that, and so that's true. Considering each variety separately, there is a positive correlation between sepal length and sepal width. That's a mistake, because if you look at them separately, they are negative. Finally, considering both varieties together, the least squares regression line for predicting sepal length from sepal width has a positive slope. That's true. So correlation and slope give you the same sign. So the answer should be D. Considering that each variety separately, there is a positive correlation between. Okay? That's that one. That gets a little confusing. It's very wordy, but I think you get it. Okay, now I want to do these, unless you have a question about that. I want to do, is this better, Leanne? Am I answering the questions that you had? I want to look at 15 and 16. Let's do 15.
Okay, so we have this equation, and x is, so as I explained in the last exercises, identify what x is and y is. That'll always help you. So x is used, which is weird, but that's what we do. We just use this here as the data or the variable to predict height. So that's going to be our x. If the Olympics had been held in 1982, which they weren't, the predicted winning height would have been, so all you do is put 1982 in here as x, and that's it. Which one do you get? Valeria gets 92.3. And that's the right answer. Okay. All right, let the fun begin. It's almost 8:30, so let's try. Any questions about that one? Very good, Alexandra. All right, so then let's try the next one. So what in the world are you going to do here? So we sort of did this in the exercise with the finance data, and just staring at it and looking at a perfect relationship told us that R was 1. Can you see that here? First of all, you need to see a positive relationship, right? Because it's a positive one. So which ones are not positive? We can cancel them by process of elimination. So which ones can we cancel that are not negative? I mean positive. For 16, Alexandra, you got A. Oh, for 16, sorry, you're looking at 16. Okay, first of all, let's cancel those that have negative relationships. So notice that all of these are going up. -1, 0, 1, that's going up. This is going up, this is going up, this is going, no, that one's not going up. And this one goes up. Okay, so as they go up, this should go up. So that's going up.
aha, that's going down. So we're going to cross that one out. That can't be it. And then these are going up. And this is going up, down, up. So that can't be it. And then this one is going not clear. 0. So if it goes up, so 0, 1, 2, this is not it either. You see? And then as -2, 0, 2, that's going up, but this is not going up. This is going, it's up, down, up. So this is out. So by process of elimination, we found it. We didn't even have to do anything else. But if you wanted to do something else, just plot it. Plot it. Plot it. Plot it. Oops. Let me do that again. So x is -1, y is 3 would be here. So what did I say? X is -1, y is 3. So it would plot like here. And then x is 0, y is 4, right? And then x is 1, y is 5. There you go. So you can see it. So I've shown you two ways of doing it. Process of elimination. Or just plotting. Got it? You can watch this video again for clarity. How about this one? For which of the following small data sets is the slope of the least squares regression line 0? When will the slope be 0? The slope will be 0 So slope will be 0 when the data is all scattered around. Like you have very small data sets here. But if there's no clear trend, the slope will be 0, right? And remember that the slope is equal to RSY over SX. So B will also be 0 if R is 0. B will also be 0 if SY is 0. These are just different instances. So what does SY of 0 mean? SY would be 0 if all the y's are the same. So which is the answer? Okay, so those are the ways that you could draw it. You could draw it to see if it's just, 3 points and they just go up and down, no trend. So it looks like D satisfies what I said here. So yeah, R is 0, SY is 0. This is a drawing of R equals 0. This is a drawing this would be a drawing of SY equals 0, right? No. Wait. I did it wrong. For all the y's to be the same, it would be like that. So in both those cases, B will be 0. Slope will be 0. So the answer is D. Are there any others you want me to try? Are there any others that bothered you? Maybe you can ask me tomorrow if you have any outstanding problems with these. So we did a few here. And that's it. There's only 23 questions. I think I did the most confusing ones, but you guys can let me know tomorrow if there's more. All right. What I want to do before you go is start probability and show you where probability starts for me. So the discussion of probability starts here. These are the probability notes. And what I want you to do for tomorrow, because I'm going to let you go now, what I want you to do, I'm going to outline the next few minutes here. These are Venn diagrams. Let's see. These are Venn diagrams. They simplify a way of looking at events. And in a space called S, the sample space of all possible outcomes. So in this sample space of all possible outcomes, there's only two possible outcomes. There's either A or B, and that's it. Because they fill the space completely, they're called complementary events. In the next sample space, there are two events possible, or there's a space around them that we could refer to as not A or B. That's how I'm going to refer. So there's three possibilities, A, B, or not A or B. If events have this relationship, they're called disjoint events. Then we have a possibility of events that actually overlap. These are overlapping events. And the possibilities are event A, event B, or event A and B, that's over here, and the other one is the one out here. What do we call the one out here? Just like we did last time, it's called not A or B. So you might have seen this terminology before, you took statistics before, and you understand it. I want you to fully understand this by next class, okay? And fully understanding it means knowing the differences between them, contrasting them. Here we have what are called overlapping events. There's no other special properties of these events other than there's A, there's B, A and B can happen, or neither A nor B. Here's also an example of overlapping events, but they have a special property known as independence. They are independent events. When events are independent, they overlap. There's the same understanding of not A or B, and there's also A and B. But there's a special quality or property about the events A and B when they are independent. So for next class, I'm going to ask you to look into this and answer these questions for me. I want you to answer, if I tell you that the probability of A is 0.3 and the probability of B is 0.4. Let me double check I want to do that. Hold on. Yes. A is 0.3 and B is 0.4. I want you to find for each of these the probability of A or B, the probability of A and B, and the probability of not A or B. And you can struggle with that a little bit to figure out what those are. And I want you to figure that out in every case, the best that you can. And we're going to talk about that tomorrow. So that's where I want you to start. So the objective is that since most of us have an intuition for probability, and that's where it comes from, but we also have errors in our thinking of probability, and I want to correct those and emphasize the intuition that you have and reinforce the intuition you have for probability. Correct the errors in thinking about probability at the same time. All right, so this is where we start tomorrow. Do your best to answer that for each of these given that information. And with that, I will say good night. Have a good rest and keep me posted if you need any help. So tomorrow we'll talk about probability, and it will also be on the test, just what we do tomorrow. There's going to be more. There's a lot on probability. I think it's one of the longer units. Okay, good night. I hope I helped.